Welcome to the 10th lecture of the wireless communication course. Today we will talk about MIMO communication. The topics of today involve the MIMO channel model, different ways of doing detection for MIMO, the use of singular value decomposition for creating parallel channels, and then beamforming, and finally capacity. These are the sections that relate to the topics as they are found in the book, so please I recommend that you go through them. And it's also maybe a good time to go through the chapter 4 of the book dealing with channel capacity. You should be able to describe SIMO, SISO, MISO, and MIMO transmission. So these stand for single input, multiple output, single input, single output, and so forth. You should be able to describe and express the general narrowband model, both geometric and Rayleigh fading. You should be able to describe and utilize different detectors for MIMO communication, and then finally apply singular value decomposition to decompose a MIMO channel and then use it to communicate over that channel, and finally perform beamforming. Before we go into more detail, let's briefly recap last time. So last time we talked about multi-user communication, where multiple users share the same channel. So that means that their communication should be coordinated. We mainly focused on cellular communication, in which case we have communication from users to the base station, but not between users. Downlink communication refers to communication from the base station to the user, and uplink from the users to the base station. We saw that in a large network there will be multiple base stations and users need to be handover between base stations. We've also seen the concept of frequency reuse, where base stations use the same frequency, but they have to be spread sufficiently far apart to not cause too much interference. For cellular communication, there are two important concepts. One is called duplexing, the other one is multiple access. Duplexing refers to the separation between uplink and downlink, and here we've seen two schemes: frequency division duplexing and time division duplexing. Frequency division duplexing is maybe easier to implement, but time division duplexing has a great benefit, and that is that you can exploit channel reciprocity, and this will be an important topic for the next lecture. Given a certain duplexing scheme, we can then define how multiple access is performed, and this refers to the sharing of resources in uplink and downlink. We've seen several schemes: TDMA, FDMA, and CDMA. There exist also other schemes. One of them is called SDMA, and this will be covered in the next lecture as well. And it's important to remember that you can combine these. So you can do TDD with TDMA, or TDMA with FDMA, or FDD with CDMA, and so forth. So any combination is possible. The mathematical model for all of these is unified, and this is in the downlink is given by this expression. So the signal sent by the base station is a superposition of signals for the different users. The signal for each user K is then a superposition of data symbols for that user and pulse shapes, and these pulse shapes are designed to have certain orthogonality properties. In the uplink, you have the signal that is sent by each user, so each user K has its own signal, and then the receiver receives the superposition of these signals, each with their own channel gain and their own delay plus noise. Now we've seen that, well, what we really want to do is, given the bandwidth that we are allocated, is to push through as much rate as we can. And we can do this by going to higher order constellations, which means that we need higher SNR. We've also seen that we can do power and rate adaptation, so that we use the good channels more and the bad channels less. We've also seen the use of OFDM to create parallel channels in time and frequency. So now we will exploit another dimension in addition to time and frequency, namely space. And we do this by using multiple antennas. The basic MIMO scheme is shown in this picture on the bottom here, where you have a transmitter with many antennas. This is what these triangles represent. And then a receiver with many antennas. And then we send one complex number per transmit antenna. The channel will then mix this information. So if we focus on what the first receive antenna sees, it is a superposition of information from all the transmit antennas. And because of that, the receiver needs to disentangle this information to be able to recover the originally transmitted data symbols. And this requires dedicated processing. And by doing this, what you can do is over the same time frequency resource, you can send multiple transmit symbols. You can boost your rate based on the number of transmit and receive antennas that you have. Of course, it doesn't make sense to have 10 transmit antennas and 1 receive antenna, because then you cannot recover your data. You should have at least as many receive antennas as transmit antennas. There are 4 different configurations that are used in the literature. So the one we've seen in all the other lectures so far was SISO, single transmit, single receive antenna, in which case there's no diversity and no array gain. There's also SIMO with a single transmit and multiple receive antennas. So then there are 2 channels, one from the transmit antenna to each of the receive antennas. In this case, we can have diversity gain and array gain. Next, there is MISO with multiple input, single output, so multiple transmit antennas and a single receive antenna. Important here is that typically the power is divided among the transmit antennas. So when we put more transmit antennas, we'll have reduced power per transmit antenna. So that means we don't have any array gain, but we can still have diversity gain, either by having channel state information at the transmitter or by having channel state information at the receiver and using something called space-time coding, which we do not cover in this course. Finally, the more general scheme is MIMO, where we have multiple inputs, multiple outputs, so multiple transmit and multiple receive antennas. The transmit power is again divided, so more transmit antennas does not give you array gain, but more receive antennas does give you array gain. So here we have the combination of diversity and array gain. And again, we have a mixing of the channels, so each antenna will receive a superposition of transmitted signals from the different transmit antennas passed through their own channel. As in general communication, the first thing you need to understand is the channel. So now we will spend a few slides on the MIMO channel. The most easy case is the so-called Freespace MIMO channel. So in this case, let's focus on the SIMO configuration because it's easier to understand, where we look at a single transmit antenna and multiple receive antennas. So the transmit antenna here is located at coordinate 0, 0. And then we have different receive antennas located at coordinate XA and XB. So it means there's a distance from the transmitter to each receive antenna given by the norm of this vector XA and the norm of this vector XB. And this then means that depending on the orientation of this receiver, so there's a certain, let me try to draw this angle theta, and this is called the angle of arrival. Yeah, this is actually not completely true. Let me carefully check this. Right, so the angle of arrival is something that's measured in the frame of reference of the receiver. So the receiver is located along this line, so the angle of arrival is measured with the orthogonal vector. So this here is the angle of arrival. And this angle here is pi over 2. So then this difference is pi over 2 minus this angle of arrival. Angle of arrival. All right, so because of this configuration, there's a certain delay difference here, which depends on the distance between this norm of XB and XA. And when the wavefronts arrive, I remember we use plane waves, so the wavefronts arrive, they will arrive a little bit earlier to antenna A than to antenna B. So the signal arrives earlier here and later here. So now let's see what happens at each of the antennas. So at antenna A, the received signal will be, well, first of all, path loss. So this here, this path loss. Then we have the delayed version of the signal. So here we see the delay. We can call this tau A if we want. And then finally, we have a phase rotation. Right, and this phase rotation depends on the distance that the wave travels. And then we can approximately write this as lambda over 4 pi times the distance, so the distance between the transmitter and the receiver, and this distance should be measured with respect to the center of the array. Then the delay will also depend only on the distance between the transmit array and the receive array, so let's call this D. And then the phase rotation. And here in the phase rotation, we don't write D because small differences in distance will lead to large rotations. So here we keep the actual distance as it is. Okay, so here we replace XA with D, and this is then an approximate expression. The same goes for the second receive antenna. So we again have the path loss, the delay, and the phase rotation. We replace, as an approximation, the distance here and here by the distance to the center of the array, but we keep the phase rotation here. Right, and now I can combine this so that the whole channel here, this is now a vector h from the transmitter to the receiver, is given by lambda over 4 pi d, because that's common to these. The delay is common, so this is a narrowband channel, so I can ignore the delay as a function of the channel. And then I have a constant phase rotation, which I say corresponds to the phase of antenna 1. So then the remaining phase is 1. And then I reduce this phase from the second antenna. Okay, so I basically say that the first antenna is reference. This one has phase 0. Right, so this is equal to e to the power j0. Then this whole thing I call the channel gain, right? Alpha, this is some complex number. And then if I look closely what this means, I can write this as a function of these angles and also of the distance between the antenna elements. So this distance is delta here. And then further, I can approximate this when, well, not approximate, this is equality. When delta is equal to lambda over 2, which is typical antenna spacing, I find this expression. Right, so the channel seen by the receiver is a complex number, and then something called the array response vector. And you can imagine that if you have more antennas, then this vector will be 1 e to the power minus j pi sine theta. On the next antenna will be e to the power j pi 2 sine theta, e to the power minus j pi 3 sine theta, and so forth. And then I can write the received signal as given by h s of t minus d over c plus noise n of t. Right, so my channel is completely determined by this vector h. Now this was for the SIMO case. You can generalize this to a MIMO case, and then you will have a channel matrix, which depends again on this angle of arrival, but also on the angle of departure. Okay, so this will be a more general case. And then if you have multiple paths, so multiple rays, then your channel will be a superposition of alpha L, A theta L, A transposed phi L. Right, so this is a matrix, which is a superposition of paths, each with their own angle of arrival, angle of departure. So this is sometimes known as AOA, AOD. So this defines the SIMO channel in free space, and then is easily generalizable to the MIMO channel in free space. And again, what matters is that angles play a role, angles of arrival at the receiver, angles of departure at the transmitter if it has multiple antennas. The orientation of the receiver plays a role, and how the antenna is placed. And this happens in this array response vector. So let's take a break and then come back with a more general model.